Hello. I'm going to go and share with you the first of the two integral theorems, and that is Stokes' theorem. And Stokes' theorem basically states that when you integrate a curl of a vector around a surface S, that would be equal to the integration of that same vector around the curve, a closed loop of that same vector. And how does that fit into the Maxwell equations? As you recall, in the four Maxwell equations, there are two that use this curl, and one state that curl of H is equal to the current density plus the derivative of the electric displacement with respect to time. And the second one is the curl of an electric field is equal to minus of the derivative of the flux with respect to time. And how would that fit? Because this is Ampere's law after the modification by Maxwell. It states that if you take the magnetic field strength integration of that around a closed curve, it is equal to the sum of all the current plus the time varying part of the electric displacement, the sum of all of that going through the surface that is defined by that curve C. So this is modified Ampere's law. And if you also take Stokes' theorem into question, which is the second part here, where we say integration of a vector around a curve is equal to the sum of the curl throughout that surface, then you will see that this part and this part is equal because they're both summary or integration of two entities around the same area on the same surface. So arbitrarily, when you reduce the surface into, instead of a quantity this much, you can shrink it to infinitesimal small area, then this one will become this one. And that's how the Maxwell equations for magnetic field strength is written in the form what we call the differential form. The same thing can be said when you talk about using Faraday's law and then rewrite it and then use and apply the Stokes theorem, and you will come out with this. Now let's go into the details of the understanding why this one is equal to this one. I use E just like for an example, but it could be very well an electric field, right? So to simplify matters, we're not going to talk about arbitrarily a 3D, three-dimension space. Now we just think about just a flat plane, XY plane. And then, of course, when we talk about that, when we talk about a scalar multiplication of two vectors like this and this, then the only thing that matters is the components of that vector, be it del cross E or be it E dot ds. The only component that we would be interested in would be the component that is in parallel with the normal to the surface, right? And then when we talk about curve, it would be in parallel to the unit vector for that curve. Okay, so the discussion here is only focused on the Z component, but you can also extrapolate that and then see that the X and the Y basically would be the same. And the way that we think about this is we're going to go and rewrite the this part here into this format. And I'm going to show you that this format is exactly the same as the definition of the curl, right? So this calculation will come out to be the same as this. So once you think about the left-hand side here as a sum of the integration of the sum of 4 components, here, 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 and each one would be an E1 times ds1. This is also a vector. E1 is a vector, and E2 and E3 and E4. Once you visualize it that way, then when you stack all these dA areas side by side, the adjacent ones will always cancel out. For example, in this dA, on this particular side, you have E2 times ds2. But on the one right next to what, on the right hand side of this one, you would have another one which is ES times minus ds. Actually, this is ds2 both, but let's simplify things, but call it ds. On y minus ds, because for that adjacent cell, this vector becomes the opposite direction. That's why the strength, the multiplication of this one is E2 times ds, but on the adjacent cell, it becomes E2 times minus ds. So therefore, if you sum up all the ones inside area like this, adjacent cells or adjacent elements of these will always cancel out. And what is left is only these components that sits on the outside where there's no adjacent cell. So obviously, when you talk about having an area and then you divide it into multiple cells like this, and I say everything internal is canceled, the only thing that's left would be the outside. So that means you're now going to be sum of all the outside. And that is what is on the right hand side. So now it would simply be saying, hey, is this truly the same as this one? It is, because E1 is EX times DX. E2, and let's look at DS3. We talked about that the last time. E3 times DS3. E3 now is similar to E1, but there's a component, since we're moving in the Y direction, so there's some changes that is made by that change. And that means the degree of change of EX with respect to Y-axis times dy. Right? So that's a change between E1 and E3. On the other hand, although because we talk about these are all vectors, so when we talk about this ds1, it is dx, but ds3 is in the opposite direction, so it's showed up as minus dx. The same thing can be said for dy, the E2 and E4 components. And when you calculate it out, some of these cancel out. The only thing left that you find is derivative of EY over X minus derivative of EX minus over Y times dx dy, which is exactly the same as the definition of the curl, the Z component of the curl of E times dA, which is, in this case, dA is the multiplication of dx times dy, okay? So, so what I had said was, if you visualize the integration of the curl as the integration of multiple little square like this, and you think of the formula for the integration is written as a summary of the 4 successive multiplication, then all the internal ones will be cancelled. The only things that are left would be the outside ones. And since the outside ones are summed up, it would be equal to this. So the bottom line is we have now just visualized that the integration of over the whole surface, called the surface S, with each component, each unit area dA, is equal to the sum of the integration of the same vector throughout the curve that defines that surface. All right, so that's Stoke's theorem. And we talk about how Stoke's theorem is used to equate the curl of H to the current density plus the time derivative of the electric displacement in the way to write it in the differential format of the modified Ampere's law, and then same thing for the Faraday's law. All right, thank you.